Hey, all right. So welcome here to the end of week number 2. And so this is Wednesday. And I guess it makes day 5 total here in summer school. Remember, Monday was a holiday. And by the way, we have a total of 17 days. And so we are on day 5. But this is a critical transition day because now, for the first time, as you and I are learning to do this remotely, we've got the big event coming on Monday. And so Monday is the exam. It is also the day when your 6 homework assignments are due for these 6 chapters, and your 4 labs are all due. And I'll say it again. Make sure that you've practiced a little bit with Canvas. I would encourage you to at least input the very first lab, and hopefully by this time you've done the 3 labs. And so go to Canvas and work on scanning them. A couple of you have sent me emails, and that's good, and I've tried to give you some guidance and some help. And some of you are still learning. You said, well, I got the lab up there, and I got it in a JPEG. I was able to take a picture of the work I did and then send that. So that's good. That's first step. And then most of you have been saying, but I'm going to work on what you said. I'm going to try to get it to a PDF because it does work better for me as a PDF. So I'm going to encourage that. So if you can get it to a PDF, great. That it really is much better. But that being said, you know, I'll take any file format. And so I know Canvas, you know, all I got to click is online, and it'll take any format. By default, it's pretty restrictive, but I've unchecked all that, and I'm just going to let you send anything you want. But like I said, much better if it's PDF. So that in mind, I'll just say that the plan today is to finish up this discussion, and I just left everything on the board from yesterday. This is the calculations we were doing, and so let's pick up where we left off on chapter 5 on gravity. As I said, it was a short chapter, so it won't take much to kind of wrap that one up. And then we'll go into chapter 6, which you'll see is on momentum, and again, that too is a short one, and so we'll wrap that one up. And then maybe we'll spend about an hour kind of summarizing these 6 chapters and kind of talking about the test and explaining the test. And I'm sure at this point you've got a lot of questions. You know, what's the format of the test? And so that's part of what I will do in the last hour of today's lecture. And so that'll probably be after the break, and so it'll be on the second part or the second lecture for today. We'll kind of give you some examples to think about, kind of summarize what we've done, and kind of explain the format of the test. But I will say right now, remember the test is Monday at 11 o'clock. And so I will set Canvas up so that the test is unlocked at 11 o'clock. And I'll set it up sometime in the next couple of days. Maybe I should even encourage you over the weekend. I'll send out an email and say, just double check that you see the exam on your Canvas page. Of course, over the weekend, when you click on it, it'll say locked until 11 o'clock on Monday, June 1. And so then right on Monday, June 1, unlock that thing, and you have an hour and a half. And on that day, on Monday, I will be sitting in front of a computer screen, either the one I use here in the lecture hall, or maybe over in my office, or maybe just my laptop. I don't know. But know this, that just in case you have questions during the exam, maybe a question is written poorly or something just goes wrong, you can shoot me off an email. And so just like in a regular face-to-face setting, I would be sitting up here and you could come up and ask me questions. Same thing. I'll just be hanging right there in front. So shoot me off an email, and I'll answer it right away and send it back. So from 11 to 12:30, while you're taking that exam, I'll just be right there looking at that email. I'll have one window open, and if somebody asks questions, I'll get to it. And if there's no questions, maybe I'll do some other work in another window there. But that's what my schedule will be for Monday. And as a side note on all that, in a face-to-face, we would have taken the test, then taken a 20-minute break, and then we would come back and do one lecture, and that's what we will also do, and that'll be on Monday. So Monday I will make only one lecture and one lab, and then of course you will take the exam, and then I will go and grade that exam. So more on the exam coming up. Let's go back here now to chapter 5, and I'll just remind you, the big picture is this. This is why it is a short chapter. It's the universal law of gravity. You take any two objects, they're gravitationally attracted to each other, and this is Newton's universal law of gravity. And so we use the gravitational constant. Then if we take the mass of the two objects, the distance between them, we can calculate the force. Yesterday we did that twice. We did it for these two spheres that were sitting over here on the edge. Maybe I'll put them back here on the edge, but I had the two spheres. They were about 10 centimeters apart, and I gave you the mass, and we did a calculation, and we came out to the force and pointed out it was a small value. Then we left off with the force between the object and the Earth, and so let me pick up there, because there is two things that are worth pointing out, or they kind of go in the same here. And if you'll let me erase this equation, hopefully that equation is buried in your mind now. And I guess we can get rid of that word vertical up there. But if you do recall from yesterday, this right here, this +1 meter, was really that extra distance here from the ground up to the center of the object. And I was asking an important question that I want to expand on here, and that is that 1 meter really important in that calculation? And I hope you can see the answer to that is no. I mean, look at what you're talking about here. This is 6.37 million meters, and then you add 1. And adding 1 just doesn't change it by much. That is my way of saying, what if I had done this calculation like this? What if I had been holding it up here, so the object is now 2 meters from the ground? What would the force be between this lead object and the Earth? And I guess what that would mean is over here, I would come and say, well, instead of being 1 meter, it's now 2 meters. And let me not take the time, but maybe if you got some extra time and you got your calculator, it can't hurt to put in this 2 meters and do this calculation, and you get exactly the same thing. You get 14.7. And the reason, of course, is you get the same thing is whether you're adding 1 or 2 meters really is insignificant compared to the 6.37 million meters that is already there in the calculation. I would even take this further and say, not just 2 meters, what if I were to take this lead sphere and go upstairs, and right above us is chemistry, and I would then say, okay, now that I'm on the 2nd floor of this building, and I go to do this calculation, instead of being 2 meters, let's see, it's probably 4, and put it on a 5, and maybe I'd be 6 meters above it. But again, I'm trying to get you to see that whether it is 1 or 2 or 6, and if I went to the 3rd story, or the 4th, now this building actually doesn't have a 4th story, but if there was a 4th story or a 5th story, or as I was in a big city with really big skyscrapers and I went to the 60th floor or the 100th floor, or even if I went to a top of a mountain at 8,000 meters, really 8,000 meters is still pretty small to this. This is a way of saying that the force of gravity, if you look technically at this equation, says that the higher I go, the further away I get from the center of the Earth, the less of the force of gravity there is. And although that's true, I want to also emphasize that as long as you're on the surface of the Earth, or even if you're somewhere within the Earth's atmosphere, if you're in an airplane and you're flying at 8,000 or 9,000 meters, you're still so short in distance away from the center of the Earth that the change in the equation between being on the surface of the Earth and being up in the airplane is so small, you're not even going to notice it. And that's why I'm sure when you've gotten on an airplane, or you've gotten into a tall building, or you've gone to the top of a mountain, you still feel like the force of gravity is still the same. And that's why we had said, before we did this chapter, if I had asked you, what is the weight of an object? Well, before this chapter, and I guess we were introduced to it in chapter 3, where we said, here's how you would calculate the weight. And had I calculated the weight before here, if I just used this, I would have said, well, the mass is 1.5. Let me grab my calculator while I'm here. The mass is 1.5 kilograms. And the acceleration due to gravity is 9.8. And so turning on my calculator and going 1.5 times 9.8, I get 14.7 newtons. And this is a way of trying to get you to see that you can hopefully begin to understand weight a little bit better than what we did back in chapter 3. Because again, back in chapter 3, this is what we did. We just said the weight was a number, and here what was calculated, and we treated it as a constant. And what I'm trying to say is that weight is really the it is the force of gravity on you from the Earth. It is this pull. It is this Newton's universal law of gravity. And so we can hopefully understand weight a little bit better, a little bit deeper, because now we see why we were able to say that the weight of the object was pretty much a constant, whether we were on the first floor or the second floor or on the top of a mountain. And the answer really is that technically the weight of something is getting less and less and less and less the further away you get. But it's not noticeable until you get so far, and what we usually like to say is out of the Earth's atmosphere. You have to get all the way out of the Earth's atmosphere. So as long as you're in the Earth's atmosphere, like flying a plane or climbing a mountain or even going down deep and digging a hole or going to, say, Death Valley, you can just treat weight as a constant number. Technically, no, it is not, but it doesn't change by much. And that's really what these numbers here are saying. And in fact, we'll watch this. If I come back here and I say ignore this number here, and so let me write it right next to this. And so if I say the force of gravity is G m1 m2 over r squared, and I put in the 6.67 times 10 to the negative 11, and then remember the units are a Newton, a meter squared over a kilogram squared. And then, of course, the mass of that lead sphere is the 1.5 kilograms. And then the mass of the Earth is the 5.98 times 10 to the 24 kilograms. And the distance between the center of the Earth and that object is the radius of the Earth, 6.37 times 10 to the 6th meters. And I'm just going to then say plus, and I won't even put a number there. You know, I'll get out my calculator and just put a 0 there. Now, again, let me emphasize, this number could be important if you got really, really far from the surface of the Earth. So if you're willing to talk about satellites or rockets and go out of the Earth's atmosphere, then I can't ignore that. But what I'm trying to show you right now is the whole reason you don't feel this effect of a changing weight when you go from the first story to the second story to the third story or up a mountain is it's just not a big enough change. And that's what I want to show you. And so I think this gives us some deeper understanding of this idea of weight and why we treated it as a constant. And it's really not. But it also gives us a little deeper understanding of where the 9.8 came from. Because watch this. Let me leave the 1.5 kilograms, the mass of the object, alone for just a second. Let me include in my calculator the other things, and so I will go 6.67 times 10 to the negative 11 for here, the universal gravitational constant. Let me take the mass of the Earth, 5.98 times 10 to the 24. Let me divide it by the distance between them, which is really the radius of the Earth if I don't include anything here. So 6.37 times 10 to the 6th, and square it. And the number I come up with is 9.8. And if you look at the units, it's meters per second squared. And the part I wanted you to see here is this gives us some deeper understanding of where the 9.8 came from. I would say then the 9.8, even though we didn't explain it back in chapter 2, in chapter 2, if you remember, was describing motion. We just did a lab. Our first lab was to take that bob and drop bob and come up with the acceleration of bob. So we didn't try to explain where the 9.8 came from, but I'm trying to get you to see now where it came from. The 9.8 is what we might say a combination of nature's universal law, so that's true for every planet, not just special about Earth. That's what this is. But then special about Earth is the mass of the Earth and the radius of the Earth. And so this 9.8 is a number and a weight that would only be true on the surface of the Earth. If you went really high out of the Earth's atmosphere, then you don't use 9.8 for the acceleration. Or if you went to another planet or a moon, like just our moon, you would not use 9.8. And so that's this whole idea here. And so that's kind of a little subtlety that I actually wish I had finished up yesterday and had time, but we were had gone long enough here. And so that's a really important part of this. Now, let me keep going, and I'll just put the equation back here on the board. I don't want you to forget that really, and the reason why this chapter is kind of short, is this is universal. And so if you know this, you really know the whole chapter. And so I've done two calculations with you. But let's keep in mind that where this can get a little more challenging is what if we were to do, say, this calculation, but also include the physics that we've already learned from the other chapters. Here's what I mean by this. I can think of the chapter, I think it's chapter 3, 3 and 4. In 3, we learned that acceleration is your net force over your mass. And in chapter 4, we learned about motion in space. And so we learned if something is going around in a circle, you would have this v squared over r. And here's why I picked all of that. What if I were to ask a question, something like this, and say, how fast is the International Space Station moving? And by the way, it comes to my mind because, hey, for the first time since 2011, we in the United States, we're going to actually launch a rocket today to the International Space Station with astronauts on it. So since we retired the space shuttle, we haven't been able to do that. And so SpaceX is getting ready to launch. And so it's a big historical moment. Although I think the bigger historical moment is this is really the first time that astronauts have been launched not by the government but by a private company. And so SpaceX has taken over. It's actually not in NASA's control room who's watching it. It's in SpaceX's control room. Now granted, it's on NASA facility where they launch there, but it's a very different world now. Instead of governments launching, private industries are launching. And that's different. Now private industries have been launching satellites and have been delivering cargo remotely, in other words, pilotless or remote controlled to them. So I guess maybe it's not that big of a deal. But it is a new change. It is private industry doing it, and it is going to live humans launch here today. Well, I'll keep that aside here, but let's try to answer that question. Let's try to answer the question, what is the speed of the International Space Station? And so maybe it's worth kind of drawing a picture here and go, okay, well, here is the Earth, and so I'll draw this little sphere. And what we have way above the Earth is a satellite going around. And I happen to pick the International Space Station, and so ISS here. All right, so the ISS is going around the Earth, and a question could just be, how fast is it going? How fast is it moving? And of course, the first thing that comes to mind is this International Space Station is going in a circle, therefore it needs a force. That is our discussion way back here of motion in space in chapter 4. But what we're learning here today is that force comes from the gravitational force. And so if I put those two things together, and also with this, watch what happens. If I take what I'm learning here today, that force is the gravitational constant times m1, m2 over r squared. Maybe if I put some symbolism in here, I might say, well, one of the masses is the International Space Station, and the other mass is the Earth, and then of course r is the distance between them, and so I would put those two in here. Now, putting that together with stuff we've already learned, I might do something like this. I know that force must equal mass times acceleration. That's Newton's second law. Like I said, that's the chapter 3. And then the chapter 4 is, well, wait a minute, if it's going around in a circle, I know that the centripetal acceleration has to equal the v squared over r. That's really the key to this problem, where it is asking about its speed. And so that's how I can take the new stuff that I'm learning here in chapter 5 and answer this question about speed, because there's a connection between speed and acceleration and force, and now force is what is new for this chapter. So if I come over here, I can then put m v squared over r. Now this is worth pausing and making sure we kind of understand the bigger picture, because there's an m here, but there's two m's over here. So is this a third m? Is this a different one? Or is this one of the twos? And if it's one of the twos, which one is it? Well, again, going back to this whole set of chapter 3 and chapter 4, This is the acceleration of the object. So this must be the acceleration of the International Space Station as it goes around. And so if you're going to put the acceleration of the International Space Station, then over here on this side of the equation, this must be the force on the International Space Station. Okay, so that's what that is. That's cool. But it also answers this question. This must then be the mass of the International Space Station. The force of the on the International Space Station, mass of the International Space Station, then gives me the acceleration of the International Space Station. So this is really the ISS. And so that answers that question. This is not a third mass. This is one of the two, and the one it is the International Space Station. It's not the mass of the Earth, which is really nice because then I can cancel them off since they're on both sides of the equation. And then to answer this question about how fast is the International Space Station going, I don't need to even know the mass of it. Which, by the way, is really good because that also means the speed of whatever satellite you put at this spot would be the same. It doesn't really matter what the mass of the International Space Station is. And so as we build modules to our International Space Station and it keeps getting bigger and bigger with more mass on it, the speed of it doesn't need to change. The speed is still the same. And so there's a lot of good reasons why I'm glad those cancel off. And in this case, since I'm doing a calculation, I'm just glad they cancel off because I don't have to really worry about that number. And of course, another important thing is this r. This is r squared, this is r, and a good question is, are those two r's, no pun intended there, are they the same? And the answer, of course, is yes. Maybe it's worth mentioning that, again, this right here is the distance between them. And so if I were to draw from the center of the Earth to the center of the International Space Station, that would represent the r. But in this equation here, the r is the radius of the orbit as it goes around on the International Space Station. So I would then say that this r, which is the radius of the orbit, is actually the same as this r, which is the distance between them. So I can go ahead and cancel one on each side. And then, of course, here I have velocity squared. So to get velocity, I would just take the square root. And so this is the square root of g times the mass of the Earth over the radius. And so this would answer that very important question about how fast does the International Space Station need to go. Now, as a little reminder here, we kind of mentioned this with Newton's cannon in yesterday's lecture. We said that a good way to understand this is that the object is moving, and in this case I'll have it moving to my left, and gravity is pulling it down. That makes it turn, and the whole reason it doesn't hit the Earth is it was going fast enough. And if you remember, we said that Newton calculated that speed to be 8,000 meters per second. However, little clarity here, and I'll go back to Newton's calculation. But Newton was talking about on the surface of the Earth. We are way above the surface of the Earth. But let me just show you Newton's calculation, because this is what Newton did, and he would have then used a number that is just the radius of the Earth. And so I'll do that first to show you what we were talking about and how Newton got that roughly 8,000 meters. Let me dry the board here. But then I'll go to my real question here about what is the speed of the International Space Station. So let me put V for what a satellite speed would need to be on the surface, or what I would call a cannonball launch. as opposed to what I'm really after in this problem, which is V of the International Space Station. So it would look like this. I would have this 6.67 times 10 to the negative 11. Oh, let me put in my units. This would be Newton meters squared over kilograms squared. Then the mass of the Earth, which again you don't have to memorize. I would give it to you on an exam. Of course, your exams are also open book. That's kind of new here to this remote learning. And so you can just look in your book there and get the mass of the Earth. But I would give that. And then, of course, the other thing, and I gave this number earlier too, or yesterday's lecture, or just erased it, is what is the radius of the Earth? That's the 6.37 million meters. And that would be the calculation to get something on the surface of the Earth. So let's see what that happens. But that's not what I'm after. As I said, I'm after a more realistic number about the International Space Station. So to do that one, I guess I would do the same universal constants, so the universal gravitational constant. Okay. So there's the 6.67 times 10 to the negative 11. And if we're orbiting around Earth, it would still have the mass of the Earth. And so there's the 5.98 times 10 to the 24 kilograms. And what would be different would be that the distance between them, that is the International Space Station and the center of the Earth, would be the radius of the Earth plus the altitude of the Earth. And if you remember a few moments ago, I was saying that the whole reason we can treat the force of gravity as a constant is as long as you're on the surface of the Earth, even up on a mountain or even in the atmosphere somewhere in an airplane, you're not that far up, and so the number doesn't really change. But if you caught that, I said, but outside of the Earth's atmosphere, it does change significantly, depending on how high you are. So the International Space Station is not really that high, but let's see what numbers we get. Some of our satellites are way, way out there, especially the geosync satellites. They're incredibly far out. Let's talk about those next. But in this case, I need to know then how high is the International Space Station. And the International Space Station is about 400 kilometers. And so let me just go back to chapter 1 and change my kilometers to meters. And so it's about 400,000 meters up. Again, that's not real high. Maybe to give you a picture, I'll take the globe here and say, okay, so if I take the globe, and so we take this to be the size of the Earth, the width of the state of California is a little more than this. But if I look at a globe here, and I look at the width of California, it's this little tiny amount. And so the International Space Station is really, from a perspective of this, is really just right above the surface there. But it is high enough and far enough that you'll see a calculation will change. Whereas some of our geosync satellites are like 6 times the radius of this Earth. And so, I don't know if that looks like about 6 times. And so they're really far out there. And so hopefully you're also seeing in this calculation that as they get further and further out from the surface of the Earth, making this denominator bigger and bigger and bigger, their speed goes down. So the fastest satellite we would ever have to make would be right at the surface of the Earth, which, by the way, we don't because of air resistance. And so the whole idea of Newton's cannon going 8,000 meters per second, I'll do the calculation. But you're not going to get a sustained orbit from that. It's just going to slow down. So that's why we go up so high. And so in the International Space Station's a little bit on the higher side. We don't have to quite go that high, but we call these near-Earth orbits. And you just got to get away from the air resistance drag. And then you can be any distance beyond that and orbiting. And so our GPS system is probably about this far out. Our geosync satellites are way out here. And the moon is about 30 times that distance there. So they have a lot of things orbiting the Earth. But I do wanted you to just point out the general pattern that I'm getting out of this, that the further away they are, the slower they go. And then again, hopefully that makes sense going back to our projectile motion in Newton's canon, because Newton argued that you would have to go fast enough to the left that as gravity pulled you down, you missed the Earth. And now we're learning that gravity gets weaker and weaker the higher up you go. And so if you get really high up here, because gravity's pulling you left, you don't have to travel as fast. Exactly. And so we see this in the numbers. All right, well, let me go ahead and then grab my calculator here. And so doing this calculation, 6.67 times 10 to the negative 7, 5.98 times 10 to the 24. Then divide it by 6.37 million meters. Taking the square roots of that, I get a number that is a little under the 8,000 that I was talking about. And so there would be the speed of a cannonball, the speed on the surface. Now I should also do a unit analysis here. Watch my units here. First of all, I guess I would say one of the meters down here, or there's one down here, would cancel with one up there. And then this would cancel with one there. And so what I'm left with inside here is a Newton times a meter over a kilogram. And just to remind you that a Newton is a kilogram meter per second squared, and then I'll just put the other meter over here.